Okay, now the next problem that's similar here, what we're going to look at that's different, instead of being compounded continuously, notice how this one's going to say compounded, it says 4% annually, but it is compounded quarterly. So that means I'm going to use a different formula here. I'm not going to use the continuously compounded interest formula, but just the simple compounded interest formula. So this is one of those that, again, we have to have memorized here. And it's A equals P times 1 plus R over N to the NT power. Now, the A and the P are very similar to the other formula in the fact that A is the return, P is the principal, but N indicates here the number of times in a year that it compounds. So since this says quarterly, then that will be 4. Okay, now let's actually look through the problem and fill in the other values now. So it says she's saving up for a down payment on a motorcycle. She currently has $5,290, but she knows she can get a loan at a lower interest rate if she puts down $5,807 instead. So she's got $5,290, but she needs $5,807. So she's going to initially invest $5,290. So that's going to be my principal. And so her return, she wants to be $5,807. Now, let's fill in our other values, and we're going to figure out the time, how much she needs to leave the money in there. So let's say 1 plus, here my rate is 0.04 or 4% divided by, again, the number of times that it is compounding. It's a quarterly, so this value will be 4. And then we're going to raise this to the NT power. Again, N was 4, so it would be to the 4T power. Okay, now take a look at what sort of an equation that we have to do. We have to solve for T, but notice that T is an exponent. So that means this is an exponential equation. So with those exponential equations, just like those steps that we talked about earlier, we said that we need to isolate the base and to take a log on both sides. Now this one doesn't have a base of e, so I'm not going to take a natural log. I'm going to use a common log. Now I'm going to isolate my base first. So this would be my base, whatever value this happens to be. So we're going to calculate this real quick and see what that base would be, and then we'll get it isolated. So first I'm going to enter into my calculator. I'm going to do 0.04 divided by 4, because I would divide before I would add there. And so that gives me 0.01, and then plus 1 would be 1.01. So do a little calculation there so I could see what the base was. So it's 1.01, and now that's to the 4t power. Now let's isolate that base. So I need to get rid of this 5,290. So since that it is multiplying, I can divide it on both sides. Now here's probably where I want to take this value of whatever this is and store that. So I'll say 5,807 divided by 5,290. And so that's about 1.10. Now that's not the value that I'm going to use. That's just the rounded off value. So I'm going to store that in my calculator there. Now, on the other side, well, we're left with just 1.01 to the 4t power. Now, once I got the base isolated, what I can do to solve it here is I'm going to take a log on both sides. And so now what I can do to help me solve for this t, or this unknown exponent, is to use the power property. So I'm going to get the log of 1.10 equals 4t times the log of 1.01. Now let's solve for t. So I'm going to get rid of the log of 1.01, divide it off on both sides here. Now recall that 1.01 was exact, but 1.10 was not. That was rounded off. And that's why I said when I divided this up here earlier that I stored it. So I would have all my decimal places there. So now I'm going to have the log, and then I'm going to bring up that value that I've stored by using the recall. So the log of that divided by the log of 1.01. And so here I'm getting 9.37 approximately there. And then again, I'm going to keep all my decimal places. And so that would be equal to 4t because those would cancel. And now I'm going to do 9.37112963, all the decimals in the calculator, divided by 4 now on both sides here. And so when I do that, I get the value here rounded to the hundredths place. It would be 2.34 years. So she's going to have to put the money in there a little bit over 2 years to make up the difference that she needs to get that lower interest rate. So this would indeed be in years. Okay, so those are two similar problems, but they did use different formulas. Okay, so you'll need to memorize your compounded interest formula and then your continuously compounding interest formula for both of these problems. You'll get one or the other, and you're not going to know which one. So you have to know both formulas there. Now, let's go back to some other word problems here. All right, now this is probably by far one of the toughest ones to do. This is going to take a lot of work here to show you, so just be in for the long haul here. It says a chemist running a test on an unknown sample from an illegal waste dump isolates 91 grams of what she suspects to be a radioactive element. In order to help identify the element, she would like to know the half-life. Okay, so there's the big deal. That's what we want to figure out. We want to figure out what is the half-life. The half-life is how long does it take for half of a substance to decay or to go away. Now, she determines after 80 days, only 62 grams of the original element remains. So notice here, if we go from 91 to 62, that's not even half of it. So the half-life should be more than 80 days. Now, let's see how we're going to do that, though. So it says, what is the half-life of this mystery element? So we're going to go back to our half-life formula or the population formula. It's basically the same thing here. It said the population would be equal to A naught times A to the T power. And this is where A there is a constant. Now, that's probably the biggest part of that problem is we have to find this constant. Okay, so what we can do here is substitute those two values. It's not necessarily a population formula, but it's something like this, I believe. I believe they call that A instead. That's better. And so A naught is what we start with, and then A is how much of that substance we have after so much time. Okay, so I'm going to use all those values here to help me find that constant. Now, so she started off with 91 grams, and then 80 days later, she had only 62. So 91 is the initial amount, and then 62 is what she had 80 days later. Now there again, we don't know what the constant A is. All right, and the amount of time here was 80 days. Okay, now let's solve this equation here. And notice this is not an exponential equation. I'm not going to need to have any logarithms because the exponent is known. Now, I'm going to isolate my variable here. I'm going to divide both sides by 91. So now I'll punch in my calculator. 62 divided by 91. And so that's about 0.68. Again, I'm keeping all my decimals in my calculator. Equals A to the 80th power. And now to isolate A here, I got to get rid of that 80th power. So I can do one of two things. I can take the 80th root, or what I'm going to do is raise both sides to the 1 over 80 power. So I'm going to recall this number in my calculator so that I have all the decimal places. So I'm going to say answer, and then raised to the 1 over 80 power. Okay, so this gives me about 0.9952, so forth. And really what you should probably do is go about to 6 decimal places there. Now over here, those of course would just cancel, and so there's my constant. Okay, so now that I've found my constant, I can find the half-life. So let's rewrite this formula. So we have A equals A naught, and now my constant there is that 0.995215 raised to the T power. Okay, now keep in mind what we're doing is we're trying to find the half-life. That's the amount of time that it takes for a substance, for half of the substance to go away. Now, what I'm going to do for my amounts is we can really just start with the same amount. We could do 91 grams here. But then I'm not going to do the amount that she had. Okay, I'm not going to do 62 grams, but if I want to find the half-life, then this number right here needs to be half of what I started with. So it needs to be half of what 91 was. So that would actually be 45.5. Because if I'm looking for the half-life, I'm looking for half of the substance to go away. Now the truth is, really don't matter what those two values are. Is that you're going to start off with a value, and this value is just going to be half. So if I wanted, I could have said 100, and then this value would have been 50. Okay? Or if I just wanted to make it sort of really simple, I could have made this be 4 grams, and this one would have been 2 grams. Now, when I solve this equation, I notice this is an exponential equation because the exponent is missing. I got to isolate the base and then take a log of both sides. So I'm going to divide both sides by 91. And now, since I'm finding half-life, this 45.5 over 91, or whatever this is on the left side here, is always just going to reduce down to a half. So really and truly, you could shortcut to this step right here. Okay, I could actually have started that equation from that point with that constant. Now, so it is an exponential equation. I've isolated the base. Now I'm going to take a log of both sides. So I have the log of 1/2 equals, now when I take the log of the right side, I'm going to use the power property and bring the t into the front. Now, if you're smart here, you probably stored that value in your calculator. That's going to make it easier to punch in. So now, I'm going to solve for t. So I'm going to divide both sides by log of 0.995215. Okay, so I'm going to punch it in here, and so I got log of 0.5, I'm going to say 0.5 instead of a half, divided by the log, and now I can pull up the saved version of that if I've stored it previously here. So it'd be 0.995215, or just bring it up from where you've stored it. Okay, and so to 2 decimal places, this is about 144.51 here would be my time that it would take half of it to go away. So notice that makes sense here. If it took, notice here, it went from 91 grams to 62 grams. Okay, so we're looking at it lost 29 grams, which is not close to half. So it's going to take a lot more than 80 days. And so we said ahead of time that this would definitely be more than 80 days that it would take for half of it to go away. Okay, pretty complex problem there. And so make yourself sort of a mental note here that what I'm going to have to do on this problem, this half-lives, is I'm going to have to find that constant first. Now, I will tell you this, there is another formula that you can use for this problem, but it's going to involve memorizing yet another formula. And so I've chose to go with this one. I was advised by ULM just to use this formula to solve this problem that way, because we've already dealt with that formula in a previous lesson. Okay, let's look at a couple more here now. All right, this goes back to the earthquake problem. So this is actually very similar to the one that we've just talked about a few days ago. So it says the magnitude of an earthquake on the Richter scale as a logarithm of intensity of the shock wave, the magnitude R and intensity I. The formula is R equals log of I. So they give me the formula there. That's kind of nice. So it says in December of 2001, they had an earthquake that measured 5.2 on the Richter scale. And then the Costco Junction earthquake in April of 2001 measured 3.3. So the question is, how many more times, or how much more intense was the Baja earthquake than the Costco Junction earthquake? Okay, so what I need to really find is the intensity of both earthquakes. So let's start off with the one that they gave me first, the 5.2. So let's find the intensity that is. So I'm going to use my formula here, R equals the log of I. So we know the Richter scale reading, that's what they gave us, is 5.2. So what's missing there is the intensity. So that's what I'm looking for in both earthquakes. So notice what kind of an equation this is. This is a logarithmic equation with a single log. The log's already isolated, so I'm going to go to an exponential form. So the exponential form, since this right here would be an understood base of 10, would be 10 to the 5.2 equals I. And so if I calculate here 10 raised to the 5.2 power, okay, I get a pretty big value here. Okay, so about 158,489 and then some decimals there. Okay, so I'm going to store that value in there because I'm going to need it later to compare to the other. Okay, now I've got that stored in my calculator. Okay, now let's figure the intensity on the 3.3 earthquake. Okay, so I'm going to use the same formula except for now my Richter scale reading is 3.3. So we do 3.3 times the log of I. Now I'm going to solve it the same way by putting it in an exponential form. So this will give me 10 to the 3.3 power equals I. Now if I calculate 10 raised to the 3.3 power, all right, this gives me 1,995.262315. Okay, so now this one's up on my calculator. I'm not going to store this one. Now, look at the question. I have to figure out how much more is that intense? How many times more intense is that? So notice, you wouldn't think there would be a lot of difference in a 3.3 earthquake compared to a 5.2. But notice this value is much bigger. So as the earthquake, as the Richter scale gets bigger, they are much more intense than you might think. Now, to figure out, again, how many times more intense, all I have to do is take this value here and then divide it by this value. All right, so now this one's stored in my calculator. I'm going to pull it up. Okay, and now I'll divide it by, and I've got that one stored in the answer, so I'll say divided by answer. Okay, now, so it says to 2 decimal places, and so I got 79.43 times as strong. So if you looked at 3.3 to 5.2, you wouldn't think it would be that much more intense, but it is. As the Richter scale goes up, it goes up not just by multiples, but by multiples of something to the 10th power. That's how that works. So my answer to that would be 79.43 times as intense there. Okay, the next one. Now this is actually a problem that we did, I believe, in lesson maybe 7.3 or 7.4, and it's really not any difference. So you have it's the pH problem where you can click on that, and it's going to give us the formula here that the pH is equal to the opposite log of the concentration of hydrogen ions. So this is the H, and then all the little chemistry symbols there. Now, so in this problem, when I read it here, it says that we have to find the pH of a solution with a hydrogen ion concentration of 8.7 times 10 to the negative 9th power moles per liter. It says round your answer to 2 decimal places. So I'm looking for a pH here. And so really this one's pretty simple. So pH equals the opposite log of 8.7 times 10 to the negative 9th power. And so notice this is not really a logarithmic equation because I know what that value is. All I really have to do there is just throw this into the calculator. So I'm going to punch in my negative sign and then log of 8.7 times 10 raised to the negative 9th power. Okay, so to 2 decimal places, I'm getting 8.06, which would be on the acidic side of things, so that would be an acid there. Okay, I believe that's it. Yep, that's all.